12 పైన వచ్చి మాట్లాడతారు. It's a grand welcome we bring to you this morning, filled with the desires, hopes, and dreams we all share. Good morning, everyone. I like to take this opportunity to welcome you all here today. Let us now welcome the man who doesn't need any introduction and known among of all us, and for his wise and wisdom and also his knowledge. He is none other than our beloved head of the department, Dr. Sudhir Kumar sir. And now it's time for Explore. It is a great honor for me to introduce and welcome our resource person, Dr. Jyotishwar Reddy, working as an associate professor in the Department of Electrical.
Vaishnavi, you are muted. Vaishnavi, unmute yourself. It's muted, ma.
Okay, ma'am. Sorry for this. Yeah, okay. Let us now welcome the man who doesn't need any introduction and known among of all for his wisdom and his knowledge. He is none other than our beloved head of the department, Dr. Sudhir Kumar sir. Welcome, sir. And now it's time for Explore. It is a great honor for me to introduce and welcome our resource person, Dr. K. Jyotishwar Reddy, working as an associate professor in the Department of Electrical and Electronics Engineering, Sri Vidyaniketan College, Tirupati. He received the BTech degree in Electrical and Electronics Engineering from JNTU Kakinada and ME in Power Electronics from Satyabama University and also received the PhD degree from Vellore Institute of Technology at Vellore, India. He has published his research articles in reputed journals like Elsevier, IEEE, Taylor, and Francis. His research work focused in the area of high voltage DC-DC power converters for renewable energy applications. Now I request Dr. K. Jyotishwar Reddy sir to come online and take up the session. Welcome, sir.
Thank you. So, very good morning, all. So, so in today's session is related to the modeling and analysis of the high voltage gain DC to DC converters for the fuel cell applications. So, in this session, we'll discuss about what is the need of the high voltage gain DC to DC converters for the fuel cell applications. Okay. So what is meant by high voltage gain? So why we need to boost the uh, more voltage compared to a conventional boost converter. So and how the duty cycle plays a major role in the controlling of the output voltage of a boost converter. So we'll see in this
Sorry to
today's
disturb
session.
you, sir.
Okay.
Uh, sir, your voice is
Okay. Tell me
getting
now.
disturbance, sir.
So now it is audible now.
Some disturbances, sir. Vibrating voice is coming.
So still, then wait a second. I will check log in my laptop.
Yes, sir. Sir, unmute your mic, sir. It's not audible.
And now it is audible.
Yes, sir. It's audible, sir. Thank you, sir.
Is there any disturbance?
No, sir. It's clear,
Okay,
sir.
okay, thank
Thank
you.
you.
Thank you. Okay. See, so in today's session, we will discuss about the high voltage gain DC to DC converters for the renewable applications. Okay. So what is meant by the high voltage gain? So why it is needed in the DC to DC converters? So for the renewable applications. Okay. So how we have to derive the expressions for the voltage gain. So voltage gain for the DC to DC converters. So we'll discuss in the today's class. Okay. So there are different types of the voltage boosting techniques are available, such as interleaving technique. So by using the switched capacitor and by using the coupled inductors and by using the hybridization of converters. Okay. So there are different types of the voltage boosting techniques are available. So in today's session, we will discuss about the any two among all the different voltage boosting techniques. So we will discuss about those interleaving technique and the hybridization of DC to DC converters. Okay. So by using these two techniques, how we are going to increase the voltage gain of the DC to DC converters with a less duty cycle. Okay. So due to the emerging demand of electricity and the limited stock of the fossil fuel, the most of the automakers and the power producers are looking for the renewable-based power generations. Okay. So the renewable energy sources such as the fuel cell, photovoltaic are going to lead the power demand in the upcoming years. See here, so the output voltage from an individual PV panel will be in the range of 20 to 60 volts. Okay, so it is in the range of 20 to 60 volts. So in order to use this 20 to 60 volts in high power applications, such as in the grid connected system or in electric vehicle systems or in hybrid energy storage systems. So we have to boost this 20 to 60 volts in order to from 300 volts to some 500 volts DC voltage. Okay. So by using a conventional boost converter, so the this 20 to 60 volts, we have to boost up to 600 volts, means it will be very difficult. Okay. So we should have some high voltage, so high duty cycle. So how the duty cycle plays a role in the boosting the voltage, we'll see in the coming slides. Okay. So but we can remember that, so if the duty cycle of the converter will increases, means the efficiency of the converter will decreases. Okay. So in order to boost this 20 to 60 volts by using the conventional boost converter, we should have some high duty cycle. Okay. So our main aim of this session is to decrease the duty cycle of the converter, and we should get a high voltage gain. Okay. So this is our main aim of this session. Okay. So in order to get with less duty cycle with a high output voltage, so the researchers have designed some high voltage gain DC to DC converters, so which are employed in between the PV panels and the inverter load combinations. Okay. So before going for the high voltage gain DC to DC converters, we should have some basic knowledge about the voltage gain DC to DC converters. Okay. So in order to
Hello. Hello, sir. Meeting is not there, sir. Meeting lo లేదు, sir. Sir, voice is not audible.
Okay, okay. I'm not sure. So now it is audible now.
Yeah, yes, sir. Yes, sir.
Okay, okay. Ma'am, can you please text me? Don't call me. I'm sharing my mobile network. So if you call me, the network will be disconnected.
Okay, okay, sir.
Okay, okay. Thank you. See, so this is our conventional boost converter. So it consists of an inductor, a switch, and a diode, and this will be your output capacitor, and this is your load. Okay. So here we are for the switch, we need to give that duty cycle. Okay. So that duty cycle will controls the output voltage of your converter. If the duty cycle will be high, means the output voltage will be high. If the duty cycle of the converter is less, means the output voltage will be very less. Okay, so this is for the a conventional boost converter. Okay, see here there are two modes of operations are available for the boost converter. So when the first mode of operation is when the switch is in on condition, and the second mode of operation is when the switch is in off condition. Okay, see here, so this will be our the first mode of operation. So when the switch is in on condition, so the switch will be a short circuited. Okay, the switch will be short circuited like this, and automatically the diode D will be in the reverse bias condition, hence it will be a open circuited. So all of you know that, so the always the current tries to flow through the low resistance path. Okay, so here the switch gets short circuited, here we'll get a low resistance path. So the total current will tries to flow through this a short circuited path. So now we can observe here, so the input voltage and the inductor both are in parallel. Okay, so the input voltage and the inductor both are in parallel. So the input voltage is equal to the voltage across the inductor. So therefore V in is equal to the VL I am writing here. Okay, so we know that what is the voltage across the inductor? The voltage across the inductor will be, so L into DIL by dt. So L into DIL by dt. So L into DIL by dt is equal to the input voltage, so VL. Okay, so here I am writing the dt in terms of the capital D into T. So how we are writing? So the turn on time in terms of the dt. So here we have to observe here. So we know that, so what is the formula for a duty cycle? So duty cycle D equal to the T on divided by the total time period T. Okay, so here I'm not able to write. So the duty cycle D is equal to the turn on time divided by total time. So D equal to the T on divided by T. Okay, so from this, so we can write that T on period, T on is equal to the duty cycle D into the total time period T. So here we are calculating this formulas for the turn on time. So hence I have, so here small dt is nothing but the time period during the switch in on condition. Okay, so when the switch on condition, so we can replace this small dt in terms of the, so capital D into T. So how we are replacing this in place of dt, how the dt is coming here? So that duty cycle D is equal to the T on divided by the total time period T. So what is the on time period T on equal to the duty cycle into the time period. So hence it will be replaced with, so D into T. So so bring this L into this side. So delta IL by dt is equal to so V in divided by R, V in divided by L. So this is for when the switch is in on condition. This is for when the switch is in on condition. So similarly in the second case, so when the switch will be in the off condition. Okay, so the switch will be in off condition means it will be the open circuited, and automatically the diode D will be connected. Okay, so this is the equivalent circuit diagram for when the switch is in on condition. So we can observe here, so by applying the KVL, so can you write the voltage equations for the circuit diagram? So we know that from the KVL, the input voltage equal to the voltage drop across the elements. See, so V in is equal to so the supply voltage V in equal to the voltage across the inductor plus voltage across this resistor. Okay, so V in equal to the voltage across the inductor plus the output voltage V naught. Okay, already, so from this write the equations for the voltage across the inductor. So VL equal to so V in minus V naught. So VL equal to V in minus V naught. Already we know that, so VL equal to L into DIL by dt. So here the dt is nothing but the time period during the turn off time. Okay, so here the dt is nothing but the time period during the turn off time. Okay, so what is the turn off time? So from the duty cycle formula, write the equation for the turn off time. So from duty cycle D equal to T on divided by the total time period. The total time period can be written in terms of, so T on plus T off. So from this, derive the expression for the T off, it will come as, so 1 minus D into T. So it will come as, so 1 minus D into T. So hence I have replaced the time period during the turn of time with, so 1 minus D into T. So V in minus VL, V naught by L equal to the, so DL. So this is when the switch is in off condition. So for any steady state condition, so delta IL in the closed condition, some of the current in the closed condition and some of the current in the open condition can be equal to the 0. So or else we can apply the voltage second balance for this equation. Okay. So here we will see this one, and for the coming converters we will apply the volt second balance principle for the obtaining the voltage gain formula. Okay. So you apply the delta IL in the closed condition and the delta IL in the open condition we have derived here. So just apply those, substitute those formulas, and we'll get the V naught by Vn is equal to the, so 1 minus D. Okay. So here the D is nothing but the duty cycle. Okay. So here the duty cycle plays a major role. So in order to control your output voltage. Okay. See here. So V naught by Vn is equal to the, so 1 by 1 minus D. So 1 by 1 minus D. So first suppose if the duty cycle is 0.1. So first suppose if the duty cycle is 0.1. So what will happen to the voltage gain? The voltage gain is nothing but the V naught by Vn. So if the duty cycle is 0.1, what will happen? So 1 divided by, so 1 minus 0.1. So 1 divided by 0.9. So it will become as, so 1.11. So the voltage gain will be 1.11. So which indicates that, so the output voltage is, so 1.1 times of your input voltage. So have you understood or not? See, first suppose if the duty cycle is 0.9, if you take now the duty cycle varies in between 0 to 1. So now if you take the duty cycle 0.9, if you take the duty cycle as 0.9, 1 divided by 1 minus 0.9, it will be 0.1. So 1 divided by 0.1 is equal to the 10. So which means that the output voltage is 10 times the input voltage. So here the duty cycle plays a major role. If you increase the duty cycle here, automatically the output voltage is increasing. So if you decrease the duty cycle, means the output voltage is decreasing. So but here there is one major drawback here. See here, if the duty cycle, so 0.9 means, so what will happen to the switch? So if the duty cycle is 0.9 means the switch will be on for the 90% of time. Okay. So have you understood or not? So the duty cycle is 0.9 means the switch will be on for the 90% of time and off for the, so 10% of time. So similarly, if the duty cycle is 0.5 or 0.6 means, so it will be on for the 60% of time and off for the 40% of time. Okay. So if the switching on time will be more means the stress on the switch will be very high. Okay. So if the switch is in on condition for more time means automatically the voltage stress on the switch will be very high. So our main aim is to decrease the voltage stress on the power semiconductor device. So we have to decrease the duty cycle of the converter. Okay. So similarly, if you observe in the boost converter, if you decrease the duty cycle of the converter, what is happening? The output voltage is decreasing. So but we should get a high voltage gain and we should get a high output voltage at a less duty cycle. Okay. So we have to design a DC to DC converter in such a way that, so the duty cycle should be low and the output voltage must be high. Okay. So how we can design those DC to DC converters, we will see in this slides. Okay. So coming to the high voltage gain DC to DC converters, so these are also called as a high step up DC to DC converters. Okay. So normally the output voltage of a fuel cell or PV are in the range of, so 20 to 45 volts. So in order to step up this 20 to 45 volts to a 400 or 600 volts DC application, such as in a grid connected system or in a electric vehicle application, so we should use the high voltage gain DC to DC converter. So how we achieve this high voltage gain DC to DC converters are, so there are different boosting techniques are available. So there are different boosting techniques are available. So the first one is the interleaving technique, and the second one is the The first one is the interleaving technique, and the second one is the switched capacitor. The third one is the coupled inductor. So on the voltage multiplier cell and the integration of or hybridization of DC to DC converters. So among these five types, so here in this today's session we'll discussing about the first one and the last one. Okay, so interleaving technique and the integrated or the hybridization of converters. Okay, the switched capacitor and the coupled inductors and the voltage multiplier cells are nothing but, so we are adding a switched capacitor or already we know that the switched capacitor. So what is meant by switched capacitor? Okay, so if you add a switched capacitor circuit to a boost converter means, so it will increase the voltage gain. So see here how the voltage gain will be increased by using these techniques. So the first one is the interleaving technique. So normally interleaving is nothing but so interleaving boost converter is nothing but the parallel connection of the conventional boost converter. Okay. See here, so this will be your one boost converter. So this inductor, the switch, and this diode D2. So it will form a first DC to DC boost converter. Okay. So if you observe the second DC to DC boost converter, so here one inductor, so on the diode D1 and the switch S1. So this will form a second boost converter. So we are placing these two converters in parallel. Okay. So by placing these two converters in parallel, so we are increasing the voltage gain. See here, the major advantage of this converter is we can observe here at the input side how the inductors are connected. So at the input side, how the inductors are connected, the inductors are connected in the parallel. Okay, so inductors are connected in parallel. So whatever the supply current can be shared between these two parallel paths. So these two parallel paths. So the advantage of this interleaving technique is, so the current will be shared between these two parallel paths, hence the input current ripples will be reduced. Okay, so the current is sharing between these two parallel paths. Okay, so automatically the current ripples will be reduced in the at the input side. So this type of boost converter is specially suitable for the fuel cell applications. Okay, so compared to the PV system, the fuel cells, this converter is very much suitable for the fuel cell applications. So why? Because so the fuel cell is
Hello.
So this is our modified interleaved boost converter. So here I am having the, so three inductors are connected in the parallel and the three switches and the three diodes. Okay, see here. So for the three switches, the how many gate pulses are required? So for the three switches, we require the normally we require three gate pulses to turn on the switches S1, S2, and S3. So this is the gate pulse pattern that I have taken. So I have used only the two gate pulses. Okay. So the first gate pulse, the VG1 is the first gate pulse that I have given to the switch S2. Okay. The first gate pulse I have given to the switch S2. Okay. And the
Sorry for
second
the
gate,
disturbance, sir. So can you make it as a full screen, sir?
so okay, ma'am. So the second gate pulse with a 180-degree phase shift to the first one. So see here, this is our the second gate pulse, which is so 180-degree phase shift. So with the first gate pulse, I have given to the switch S1 and switch S3. Okay. So see here, have you understood or not? So for the switch S2, I have given the gate pulse with a phase shift of 0 degrees. Okay. So for switches S1 and S3, for the both the switches, I have given the same gate pulse. So with a 180-degree phase shift, which I have given to the for the switch S2. Okay. So you can give the gate pulse patterns. You can give at your convenience, but you can assure that at any time, so at least one switch should be in the on condition. Okay. So if you take the time, if you observe this at the time, so at least at any time period, so minimum of one switch should be in the on condition. So if you take this time interval, so here, so the switch, this is for this gate pulse is for the switch S2, and this gate pulse is for the switch S1 and S3. So if you take this time interval, so all the three switches are in on condition. All the three switches are in on condition. So if you take this time period from T1 to T2, so we can observe here the switches S2 and S1 and S3 are in on condition. So why? Because the gate pulse, the second gate pulse we are giving to for the switches S1 and S3. So if you observe this time period, all the three switches are in on condition. Okay. So whereas if you observe at the last time period, only the switch S2 is in on condition. Okay. So while giving the gate pulse, you should be keep in mind that so at least any one switch should be in the on condition. Okay. So you can try one more pattern for this system. So you give the three gate pulses. So individual gate pulses for switch S1, one gate pulse. So for switch S2, another gate pulse. So for switch S3, another gate pulse you can give. So with a phase shift of 120 degrees or 180 degrees. So you draw the waveform of that one with a 120-degree phase shift and draw the waveform of the gate pulse pattern with a 180-degree phase shift pattern. Observe that at all instant any one switch is operating or not. Okay. If the switch is operating at any one instant, so then go for the voltage gain derivation. Okay. So then observe what is the voltage gain you have obtained. So whether the voltage gain you have obtained is more than the conventional boost converter or not. Okay. So this is the concept. So here I have used the two gate pulses. So one is for the switch S2 and another one is for the switches S1 and S3. So for the switches and S1 and S3, I am using the single gate pulse only. Okay. So with a 180-degree phase shift of the first gate pulse. Okay. So now coming to the modes of operation. So there are totally 4 modes of operations are available. So the mode 1 and mode 3 are exactly similar. So hence I have only 3 diagrams are available here. So this is for the mode 1. So you can observe here the mode 1 is between, so from T0 to T1. So this is from T0 to T1. So from T0 to T1 we can observe that so both the gate pulses are active. So the VG1 and VG2. So both gate pulses are active. So if both the gate pulses are active means all the 3 switches are in on condition. Okay. So all the 3 switches are in on condition. So automatically the diodes will interlink to that switch will be in the reverse bias condition. So this is similar to the conventional boost converter. So we have observed that. See here. So when the switch S is in the active condition, so the here also in the same way. So when the switches S1 is turned on, automatically the diode related to the switch S1 is in the reverse bias condition. Okay. Similarly, here all the three in the mode 1, all the three switches are condition. So automatically all the three diodes will be in the reverse bias condition, nothing but the open circuit. Okay. So at this particular point, what will happen is the supply voltage. So the supply voltage increases the current in the inductor. See here. So you can observe from the graph. So I1 is the current through the inductor L1, I2 is the current through the inductor L2, and I3 is the current through the inductor L3. Okay. So you can observe from the T0 to T1. So you can observe the time period between T0 to T1. So we can observe that. So T0 to T1, so all the current through the inductors, so current through the inductor L1 and the current through the inductor L2 and the current through the inductor L3 increases linearly. Okay, so increases linear. So here the capacitor C1 and C2 supplies the energies to the load. So whatever the energy stored in the capacitor C1 and C2, that will discharges through the load V0. Okay, so here I have used the resistive load. So this will be during the first mode of operation. So in the second mode of operation, you can observe here. So this will be from T1 to T2. We can observe here the time period. So which gate pulse is active? So the second gate pulse is active. The second gate pulse is given to the which switches for the switch S1 and switch S3. So sorry. So sorry for the experiment. The second gate pulse we have given to the switch S2. Okay, the second gate pulse we have given to the switch S2, and the first gate pulse we have given for the switches S1 and S3. So here you can observe that. So whichever switch is turned on, so the diode corresponding to the switch will be in the off condition. So here the switch S2 will be in on condition. So the corresponding diode D2 will be in the reverse bias condition. Okay. So here the switch S1 will be in off condition. Automatically the diode D1 will be in on condition. So the switch S3 will be in off condition. Automatically the diode D3 will be in the on condition. Okay. So here you can observe that which switch will be in on condition. So the switch S2 is in on condition. So the inductor corresponding to that switch will be charged. Okay. So the inductor, the corresponding switch will be charged. You can observe here. So L2 is charging. In the first mode also, all the three inductors are charging. In the second mode, only the second inductor current only is charging. You can observe here. So current through the inductor L2. So this waveform. So in the second mode also, the current is increasing linearly. So have you understood that? So in the second mode also, the current is increasing linearly. So whereas if you observe for the inductor L1 and inductor L2, so the switches S1 and S3 are in off condition. Hence, automatically, so the current through this inductor will be discharged. Okay. So this is for inductor L1 and this is for inductor L2. Okay. So the current in these two inductors is discharging. So here the output capacitor C1 supplies the energy to the load. So here that output capacitor C1 supplies the energy to the load. Okay. So on the next one is the mode 3. So you can observe here. So this will be your mode 3. So from T2 to T3. So from T2 to T3, so both the gate pulses are in active. So both the gate pulses are in active. So which means that so the switch S1, switch S2, and the switch S3, all the three switches will be in the on condition. So all the three switches will be on condition. So the mode 3 is exactly similar to the mode 1. So the current through the inductors L1, L2, and L3 increases linearly. So you can observe here. So from here to here, so the current in the inductor L1, the current in the inductor L2, and the current in the inductor L3 is increasing linearly. Okay. So then both the capacitor will supply the energy to the load. So on the last one is, so the last mode is operation is exactly similar to the mode 2. So in the mode 2, you can observe here the switch S2 is in on condition and the switch S1 and S3 is in off condition. So here the switch S2 will be in off condition and the switches S1 and S3 will be in the on condition. So we can observe here the diode related to the switch S1 and the diode related to the switch S3 are in off condition. So can anyone tell that which diodes? So the current through the inductors will be increasing. So here the switch S1 will be in on condition. So hence the inductor related to that switch S1 will be increasing. Similarly, the current through the inductor L3 will be increasing. See here in the waveform you can observe here. So the current through the inductor L1 and current through the inductor L3 is increasing linearly. So whereas the current through the inductor L2 decreasing linearly. Okay. So first you should understand how the switching pattern will be available and which diode will be in off condition and which switch will be in on condition, and you have to apply the KVL for the modes of operation. Okay. So if you thorough with this the modes of operation and if you draw this waveforms, so then it is very easy to derive the expression for the voltage gain. Okay. See here. So the voltage gain of the converter is obtained by obtaining the volt-second balance principle for the inductors L1 and L2 and L3. Okay. So now we have to apply the volt-second balance principle for the inductors L1, L2 and L3. See here. So this will be the voltage across the inductor L1, and this is the voltage across the inductor L2, and this is the voltage across the inductor L3. Okay. So the volt-second balance principle means so the sum of the voltages in the particular time period is equal to the 0. Okay, the sum of the voltages of an inductor, so of a particular inductor in that time period we have to equal to the 0. See here, so the voltage across the inductor L1, so VL1, so VL1 I am equating to the 0. So voltage across the inductor L1 I am equating to the 0. Similarly, the voltage across the inductor VL2 I am equating to 0. Similarly, the voltage across the inductor VL3 I am equating to the 0. Okay. See here, now apply the volt-second balance principle for the VL1. See here, it is so from T0 to T1, so the output voltage will be VFC. The voltage across the inductor L1 will be so VFC. So VFC into this time period T1 minus T0. So VFC into T1 minus T0. Okay, so VFC plus T1 minus T0. So for the second time period, so VFC minus VCN into T2 minus T1. So VFC T2 minus T1. So for the third time period, so it will be so VFC. So VFC into T3 minus T2, and similarly, so for the last time period, the voltage will be the VFC. So VFC into T4 minus T3 equal to the 0. So if you simplify this equation, it will come as so VCN equal to the VFC divided by so 1 minus D. So where D is the duty cycle of the converter. Okay. So similarly, now apply the volt-second balance principle for the inductor L2. So for inductor L2, can anyone tell? So for inductor L2, so this will be so VFC into T2 minus T1. So sorry, T1 minus T0. So in the second interval also the output voltage is VFC. So VFC into T1 minus T2 minus T1. So for the third interval, the output voltage will be VFC. So VFC into T3 minus T2. So for the last interval, the output voltage is VFC plus VCN minus VC1. Okay. So VFC plus VCN minus VC1 into T4 minus T3. So you may have got the doubts how this VFC and VFC minus VCN are coming. So if you apply the KVL for those loops, so if you apply the KVL for those loops, you will get this equation. So VFC minus VCN and VFC plus VCN minus. So these equations are obtained by applying the KVL to that particular loop. Okay. So if you simplify the voltage across the inductor L2, it will come as the VC1 equal to the VFC by so 1 minus D plus VCL. Okay. Similarly, apply the volt-second balance principle for the inductor L3. So inductor L3, so this will be the voltage across the inductor L3. So VFC into T1 minus T0. So VFC minus VC2 into T2 minus T1. Similarly, if you apply for all the time periods, so this will be the equation 15 will be the volt-second balance principle for the inductor L3. Okay. So now we know that the output voltage of the inductor is given as so VC1 plus VC2 minus VFC. So VC1 plus VC2 minus VFC. So this is obtained so by applying the KVL for this entire circuit. Okay. So the output voltage V0 is given as the VC1 plus VC2 minus VFC. Okay. So this will be your output voltage across the inductor. So V0 equal to the VC1 plus VC2 minus VFC. So by solving all the above equations, substitute the VC1 value and VC2 value, VFC value, you will get as so V0 by VFC equal to the 2 plus D by 1 minus D. Okay, so where D is the duty cycle. So D is nothing but the voltage gain. So you can observe that for a conventional boost converter, what is the voltage gain? So G equal to 1 by 1 minus D. So here for the this modified interleaved boost converter, what is the voltage gain? So 2 plus D by 1 minus D. So if you draw the voltage gain comparison for a conventional boost converter and for the interleaved boost converter, so it will be came here. So if you take the duty cycle and the voltage gain of the boost converter and the voltage gain of interleaved boost converter, you can observe here. So for a duty cycle of 0.1, okay, so for a duty cycle of 0.1, so for a conventional boost converter, the output voltage is 1.1 times of your input voltage. Okay, so if you give a 24 volts as input voltage, then the output voltage is 24 into 1.11. Okay, so whereas if you go for the interleaved boost converter, so what is the voltage gain for the 0.1 duty cycle? So it is 2.3. Okay, so here the output voltage is how much times? The 2.3 times of your the input voltage. So this this is the tabular column for the different duty cycle. So if you observe that, so at 0.9 duty cycle, so you are giving, so the voltage gain of a conventional boost converter is 10. So whereas the voltage gain of a interleaved boost converter is 30. So it is almost 20 times, so more than the conventional boost converter. So for suppose, so here the voltage, your input voltage is 20 volts. So then what will be the output voltage of a conventional boost converter at a duty cycle of 0.9? So it will be 20 into 10, so 200 volts. Okay, so 20 into 10, 200 volts. So you are boosting the 20 volts to the 200 volts by using a duty cycle of 0.9. So whereas if you come here, so for interleaved boost converter, so here the voltage gain is 30. Okay, so your input voltage considered as a 20 volts. So the output voltage will be 20 into this voltage gain, so 30 times. So almost it is boosting up to 600 volts. Okay, so have you understood? So this is the graph between, so the same tabular column I have represented in the graph. So here it will be the duty cycle. So 0, 0 0.1, 0 0.2. So until 0 0.9, I have taken on the outer side of this one. Okay, so these are so this first line and so these are the voltage gain. So this is the voltage gain 0. So this is 5, 10, 15, 20, 25, and 30. So we can observe here. So at 0 0.9 duty cycle, so what is the voltage gain of interleaved boost converter? So this will be 0 0.9. Okay, so until here, so this black line indicates the voltage gain of your the interleaved boost converter. So this is here up to 30. So this 0 0.9 line is touching this 31. Okay, so whereas if you take for the conventional boost converter, it is only 10. You can observe here. So this is the 10 voltage gain 10. So you can observe that orange color line is up to voltage gain 10 only. Okay, so this is how we can increase the voltage gain of your converter. Okay, so the interleaving technique is better suitable for the renewable energy application. So for renewable energy application, especially for the fuel cell applications. Okay, so this is the hardware implementation. So I have done during my PhD. So this is for so I have considered for the 200 watt system. Okay, so the output voltage waveforms are not available with me, so I am not able to share these waveforms. Okay, so this is the just hardware prototype for the interleaved boost converter. So here it will be the programmable DC source. So programmable DC source, from here I am supplying the DC input voltage. See here, this will be your analog discovery kit. So from here I am supplying the gate pulses. So from this analog discovery kit, I am supplying the gate pulses to the all the 3 switches. Okay, so instead of this one, you can use the DSpace or any microcontroller for generating the gate pulse. Okay, see here. So one important thing I am going to share with you. So first, when you are doing a research on the DC to DC converter, so if you want to publish a paper on the DC to DC converter in any impact factor journals or in any reputed journals, so like elsewhere or Thailand Francis or IEEE, so you should model your DC to DC converter and you have to verify the your converter is better suitable for any renewable applications. Okay, so first design your converter. So derive the voltage gain equations on the inductor and the capacitor, modeling of the inductor and capacitor. So then apply for the any renewable application. So whatever. So here, so this is the work due to my PhD. So this is the fuel cell I have taken. So I have considered the renewable source as a the fuel cell. So this fuel cell I am integrating to the a DC to, for a grid connected system. Okay. So what are the things we have needed? So one is the interleaved boost. So one is the high voltage gain DC to DC converter, and another one is the inverter. Okay. So my main research topic is, so here I am going to, my research topic is to design the high voltage gain DC to DC converter for the fuel cell application system. So if you design your DC to DC converter, and if you write a paper, and if you communicate for any journal, so it won't, so maximum it won't accept. Okay, so you should integrate to any one application. So whether it may be a grid connected system, it may be a DC. If it is a DC source, you can integrate a DC grid, or if you again if you use an inverter, and you can integrate to the AC grid, and you can connect to a three-phase grid connected system. Or similarly, you can the same concept you can integrate to a electric vehicle application, or any for the solar water pumping system. So wherever, if you design a DC to DC converters or multi-level inverter topologies, so if you get a paper in some reputed journals, you should go for the application oriented. You have to write your paper in application oriented. So then only your paper will get accepted. See here, this is my second work. Here I have integrated the fuel cell source. So the concept will be same. So I have designed the converter. So this converter I have integrated to a BLDC motor, so which is mostly using in the electric vehicle application. Okay, so electric vehicle. So for this I have designed a controller, and for also for voltage gain converter I have designed a controller. Okay, so similarly you can apply for the hybrid DC hybrid PV PEMMC system. Okay, so here I have used the PV source and the PEMMC. So here we can use that high voltage gain DC to DC converter. So for the PV source, we can use the high voltage gain DC to DC converter source, and the PEMMC source also we can use the PEMMC source. Okay, so keep it in mind. So if you want to publish a paper, you should write the paper in terms of application oriented, especially for the power electronics people. Okay, so this is for the interleaved boost converters. So if you have time, so try to do the analysis of the converter. See here I have given the gate pulses, 2 gate pulses I have given. So one is for the switch S1 and S3, I have given the same gate pulse. The second gate pulse I have given to the switch S2. Okay, try to do with the 3 gate pulses. Okay, so 3 gate pulses for the switch S1, and for the switch S2, and for switch S3, 3 different gate pulse you can give the gate pulse. The phase shift may be your choice. You may give the 120-degree phase shift, or you may give the 60-degree phase shift. So, but you can assure that at least one switch should be in on condition at any particular time. Okay. So, if you have any doubts regarding this, you can mail to me. So, I will help you. Okay. So, the next concept is the hybridization of converter. So, the hybridization of converter is nothing but the integration of 2 converters. So we are integrating the 2 converters. So we are joining 2 DC to DC converters. Okay. So there are different types of converter, zeta converter, and lot of DC to DC boost converters are available. Okay. So here hybridization of DC to DC converters are nothing but integrating. So we are integrating the 2 converters. Okay. So then the output voltage will be the sum of the 2 converters. Okay. For suppose if I integrate the boost converter and the cut converter, so in a single circuit diagram, so then the output voltage will be the sum of these 2 output voltages, the sum of the boost converter output voltage and the sum of the cut converter output voltage. Okay. So, we know that. So these are the circuit diagrams for the first one is the circuit diagram for a conventional boost converter. Okay, so what is the voltage gain of a conventional boost converter? V naught equal to V naught by Vin equal to 1 by 1 minus D. So this is the second boost converter, which is nothing but a SEPIC converter. So this is the SEPIC converter. So for this, the voltage gain G is equal to the D divided by, so 1 minus D. So the next one is the Kirk converter. So for this one, the output, the voltage gain G is equal to the, so minus D divided by 1 minus D. And this is another boost converter, zeta converter. So for this, the output voltage gain G is equal to the D divided by 1 minus D. So now what we are going to do is, so we have to integrate, so any two converters, okay. So for suppose I will integrate the boost converter with a SEPIC converter. So then the output voltage will be the sum of, so this boost converter and the SEPIC converter. Okay, so we can integrate these two converters, the Kirk converter and the SEPIC converter. So the output voltage will be the sum of the SEPIC converter plus Kirk converter. Okay. See here, the first one is the integration of the boost and the Kirk converter. So the integration of the boost and Kirk converter. So we can observe here whether any boost converter is present here. So this is the combination of both boost and Kirk converter. So just keep it in your mind. So what is the boost converter circuit diagram and what is the Kirk converter circuit diagram? So see here. So this inductor, so this switch and this diode and this capacitor forms a boost converter. Okay. See here. So what is the circuit diagram of boost converter? So first you start with a inductor, a switch, and a diode and a output capacitor. Okay. See here. So this will be inductor, a switch, and the diode, and here it will be output capacitor. So this is our boost converter. Okay. So here I am integrating the boost converter with a Kirk converter. Okay. So a Kirk converter. So what is the Kirk converter? So here it will be a Kirk converter. Okay. So it is the combination of inductor, a switch, and a capacitor and a diode. After that, two inductors are there. Okay. So see here. So inductor, this capacitor, switch, and the capacitor, and this will be the inductor, the second inductor, and this will be the diode, and this will be the output capacitor. So have you observed that? So what is the advantages of the integration? So the complexity. So here if you separately join these two converters in a parallel means, so we should get two switches. So if you take the boost converter and a Kirk converter here integrated, if you on the output side, if you join the voltages parallelly means, so then what will be the disadvantage means there will be the more number of switching devices. So here one switch is available. So here also one switch is available. So what is the how many switches? Two switches. And the diode and inductor components will also be increased. So but here you can observe that, so the single switch is using for the both the converters. Okay, the single switch is using for the both the conductors. So this first inductor is commonly using for both the boost converter and also for the Kirk converter. Okay, so this is our integrated boost and Kirk converter. So the voltage gain of this one is the G is the 1 plus D divided by 1 minus D. Okay, so if you derive the expression for this one, the voltage gain will come as a, so 1 plus D divided by, so 1 minus D. Okay, so the next one is the integrated, the boost and SEPIC converter. Okay, the second one is the, so this is the combination of both boost and SEPIC converter. So you can anyone observe, so where the boost converter is present here? So for the boost converter, first inductor will come, so after that switch, after that diode. Okay, see here. So this is our supply voltage. So from this it will come as an inductor, so switch, okay, diode and the capacitor. Okay, so this will be your the boost converter. So you can observe the SEPIC converter here. Okay, so this will be your SEPIC converter. So inductor, the switch, and the two inductors. Okay. Okay. So this will be inductor 1 and this will be inductor 2. And the switch is using commonly for the both the converters. Okay. So this is for the integrated, the boost and SEPIC converters. So here also the voltage gain is similar to the first one. So the voltage gain is 1 plus D divided by, so 1 minus D. So we can again draw the graph for this one. So by placing the D equal to duty cycle from 0 to 0.9, you can observe so what is the voltage gain. So whether the voltage gain is more than compared to the conventional boost converter or not. Okay, so it will come, it should get greater than the conventional boost converter. Why? Because it is the integration of the two converters. So it will come as the output voltage of the boost converter as well as the output voltage of the converter. Okay, so draw the graph and observe the duty cycle waveform for the both the converters. So and this is the integration of all the converters. So here I am integrating the three converters. So boost converter I am integrating, the SEPIC converter I am integrating, and the CUC converter I am integrating. So for this one, so the voltage gain is come as the 2 plus G divided by 1 minus. Okay, so I will explain any one converter in this session. So how to derive the expression for this, the voltage gain. Okay, so on the last one is the integrated boost and self-lit SEPIC converter. Okay, so for this the voltage gain is the G is equal to the 2 divided by 1 minus D. So there are number of hybrid DC to DC converters are available for in order to getting the high voltage gain. Okay. See here now we'll discuss about the one converter. So this is the integration of a modified SEPIC converter and conventional. Okay. See here. So this is it is the combination converter. So this is the combination of the CUC converter and a conventional boost converter. So wait a second, whether the meeting is sharing or not.
It's visible, sir.
Okay, thank you. So this is the combination of both the CUC converter and the conventional boost converter. See here, so from here you can observe that. So this will be your inductor. Okay, so this is inductor and this is your switch and this is the diode and this is the output capacitor. So this combination is entire thing is a conventional boost converter. So this entire thing is the combination of a conventional boost converter. So for this I am integrating a CUC converter. Okay, so a modified a CUC converter. So for this one, so how we will derive the voltage gain, so we'll see here. So how many switches are there here? So both the switches are in on condition, and the second mode of operation is when both the switches are in off condition. Okay, see here. So this is the gate pulses I have given for the circuit. So this will be this is from 0 to T1. So both the switches are in off condition. From T1 to T2, both the switches are in on condition. Like so, you can choose any gate pulse. Okay. See now in the first mode of operation. So we have observed that. So we can consider that the switches S1 and S2 are in on condition. Okay, so the switches S1 and S2 in on condition. So then the diodes corresponding to the D1 and D2 are the switch S1 and S2 are in reverse bias condition. So for this condition, so we have to derive the expression.
I request Manideep sir, please unmute yourself. Sir, mute yourself, sir. Manideep sir, please mute yourself. Manideep sir. Hello. Sorry for the inconvenience for the participants. I think resource person having some technical issues. So we'll wait for 5 minutes. Session is not yet completed.
See here for the, so again I'm repeating it's for the mode of operation for the so first mode of operation and the second mode of operation. So in the first mode of operation, the both the switches are in on condition. So for that we have to write the voltage across the inductors. So how many voltage, so inductors are available here, so two inductors are available. So for the two inductors we have to write the formula. So one is for the voltage across the inductor L1 and voltage across the inductor L2. Okay, so by using the KVL, so we have to write the formulas for the voltage across the inductor L1 and also voltage across the inductor L2. Okay, similarly during the mode 2 of operation, okay, so both the switches S1 and S2 are in off condition. Okay, so now write down the expressions for the voltage across the inductor L1 and voltage across the inductor L2. Okay, so while you should thorough with the KVL, so then only it is easy to write the voltage equations. Okay, so now write down the equation for the voltage across the inductor L1. So voltage across the inductor VL1 is equal to the, so VFC plus PC. So voltage across the inductor L1 is equal to the, so this supply voltage VFC plus and this capacitor voltage Vc. Okay. Similarly, the second inductor is VL2. The voltage across the inductor VL2 is equal to the VFC minus V naught. So the voltage across this inductor is VFC minus this voltage across the output resistor. Okay. See. So now apply the volt second balance principle for the inductors. Okay. So now apply the volt second balance principle to the inductor. So VFC into dt. So what is the time period? So limitation we have to type 0 to kts. So here k is nothing but the duty cycle. So in some papers it may be represented with d, and in someone can represent it with k. Okay. So VFC into kts plus the integral of kts into ts. So VFC plus VC. Okay. So one is for the during the switch this is for the inductor L1. Similarly, by employing the volt second balance principle for the inductor L2. Okay. So this will be the volt second balance. So 0 to kts is nothing but the switch on time period. So kts to ts is nothing but the switch off period. Okay. So if you take for inductor L1, so the what will happen to the inductor L1 during the we have to consider the total time period, the switch on time period plus the switch off period. So here I have, so this is for the voltage during the switch on condition. So this is during the switch off condition. So this is for the inductor L1. Similarly, for this is for the inductor L2 after applying the volt second balance. This is for the switch S2 when the during the switch on conditions, and this is for the inductor L2 when the switch is in off condition. Okay. So if you simplify those both the equations, you will get the duty cycle equal to the 1 divided by 1 minus k whole square. Okay. So this is the comparison of the voltage gain. So this is the comparison of the voltage gain for a conventional boost converter and a high step up interlevel boost converter and the hybrid boost converter. So you can observe here. So from this we can observe here up to 0.5 duty cycle you are getting the same boosting technique for any converter. Okay. So the voltage gain is almost similar for all the converters. So from 0.6 to 0.8 or 0.9 only the voltage gain is rapidly varying for the high voltage gain converters. Okay. So if you take at the 0.7 duty cycle, so 0.7 duty cycle, so your conventional boost converter is getting very low voltage gain. Okay. So after that, if you take the interleaved boost converter, it is getting somewhat higher than the conventional boost converter. So next one is the high step up boost converter, which is nothing but the hybrid DC to DC converter. So it's getting more voltage compared to the all other two converters. Okay. So from this we can conclude that, so if you take a duty cycle, so we at least we should get from 0.6 duty cycle or 0.7 duty cycle. Okay. So then only your output is getting more duty cycle. So if you want to reduce the duty cycle less than 0.5, so and you have to and you should need a high voltage means it is not possible. Okay. So from 0.9, so if you want to use a conventional boost converter, so the conventional boost, the duty cycle will be 0.9 in order to get a voltage gain of 10. Okay. So whereas by using this in high voltage gain DC to DC converter, so at the 0.7 itself we are getting a voltage gain of 10. Okay. So from 0.9 to we have reduced the duty cycle up to 0.7. Okay. So still the research is going on to decrease this voltage gain. So until further the 0.6. Okay. So this is the same hardware implementation for this interleaved boost, for the hybridization of DC to DC converters. So here it is the integration of both the boost converter and the cut converter. Okay, so this is also designed for the 200 watts. Okay, so one more important point I am going to lead. So if the three switches are there, so a simple way is there to give the gate pulses for during in the MATLAB. So I will share that screen. Wait. So this is your, so this is the interleaved boost converter, the first converter I have discussed. See here, how many switches are there here? So three switches are there. Okay. So in the MATLAB, so very simple technique is there for giving the gate pulses for the three switches. So if it is a one switch is there means, so no problem, we can directly use some pulse generator, or directly we can give the waveform. Okay. So if you have a three switches and you have to give a gate pulses for the converters means, so it will be very difficult. So you have to write a coding, or you have to manipulate in the pulse generator itself. Okay, so you have to calculate from which time period to time period it will be on. So so it is a very lengthy process to give the gate pulses. Okay, see here. So one block is there. So that is called as a PWM generator DC to DC. Okay, so search it in the MATLAB Simulink. So you'll get this block here. Okay, so PWM DC to DC generator. So if you double click on this one, so you can get so what is the switching frequency you need. So from 10 kilohertz or 100 kilohertz, anything you can do. So based upon your requirement. So this is the duty cycle I have given. So the duty cycle I have calculated, it is for 0.678. Okay. So the 0.678. So this I have given for the first gate, first one. Okay. So we can observe here, this is the second gate pulse. Okay, so this is the second gate pulse for the second switch. So just click on this arrow mark, so you will get. Okay, so one more time I'm repeating here. So just click on this arrow point. So look inside the mark, it will come. So here there is a sawtooth generator waveform is there. Okay, so if you double click on this one, so here there is a call as a phase, so phase shift. So in terms of degrees. Okay, so if you may give it 120-degree phase shift or with a 180-degree phase shift. So whatever the phase shift you needed, so we can give here itself. Okay, so this is very, very simple technique for generating the gate pulses if the more than two switches are available in a converter. Okay, so no need to use of a pulse generator. And if you use a pulse generator, it is a very lengthy process to calculate what is the phase shift, and everything is a very big process. Okay, so this is for the second one. Okay, so if you want to go for the third switch, so here it is the third switch. Look into the mask. So for the third switch, I have given it a phase shift of 240 degrees. Okay, so for switch S1, I have given the phase shift with 0 degree. For switch S2, you can give the phase shift of 120 degree. For the switch S3, I have given the phase shift of 180, so 240 degrees. So RS, so in the while discussing the circuit diagram, I told that so for the switches and S1 and S3, I have given the same gate pulse, which is so with a 0 degree phase shift. So I can change here. So for switch S1 and switch S3, it is 0. Okay. So whereas for switch S2, it will be so 180 degree. Okay. So just directly give to the gate of the MOSFET or IGBT. So automatically the gate pulses are generated for this circuit. Okay. So this is how we need to give the gate pulses for the circuit in the MATLAB in a simple way. Okay. So I hope this will be very useful for you. Okay. So now for the application oriented, so we can use in a grid connected system applications, or in electric vehicle applications, or in solar water pumping system, or in a hybrid energy storage system. So okay, see here, so the electric vehicle application and the solar water pumping system, both the applications are exactly similar. So the only thing is, so there also you use the BLDC motor. Here also in the electric vehicle applications also you are going to use the BLDC motor. So here, okay, so the converter will be same. So the inverter you are going to use the same. So and the motor is also same for both the electric vehicle applications and also in the solar water pumping system. Okay. So you should write a paper in related to the application oriented. So then only your paper will get. So if you have any doubts, you can ask. So if you have any queries, so you can mail to me. So my mail ID is
Sir, one question. Sir, sir, some
ah,
question
tell me.
is posted in the chat box. Shall I read that one, sir?
Ah, tell me.
What are the application of hybrid converter?
So applications of hybrid converters is nothing but so we should get a the high voltage gain for the renewable applications. So already I told that. So if you take so here we are getting the output voltage of a PV panel is around the 20 to 60 volts. Okay. So if you use a conventional boost converter, so what is the maximum voltage gain of a conventional boost converter? So you can observe from this table. So if you use a conventional boost converter, so the maximum voltage gain is so 10 volts. Okay. So your PV panel input is so from varying from 20 to 60 volts. So for suppose if we consider a PV panel voltage is so 20 volts. So if you by using a conventional boost converter, we can boost the voltage up to 200 volts only. So why? Because the maximum voltage gain of a conventional boost converter is 10. So 20 into 10 is 200 volts. So what is the duty cycle of that one? It is a 0.9 duty cycle. So if that duty cycle is 0.9 means so 90% of time period, so the switch will be in the on condition. Okay? So only 10% of time the switch will be in the off condition. So which means the switching stress on the MOSFET or IGBT is increased. So which will decreases the efficiency of the converter. Okay. So by using the hybrid converters, so we are integrating the two converters. So integrating two converters. So which means that the output voltage is the sum of the two converters. So the automatically the voltage gain is increasing so with a lesser duty cycle. Okay. So with a lesser duty cycle, it is around some 0.7 or zero point 0.6, it may be around 0.7. So 0.75 duty cycle means only 75% of your time period, the switch will be in the on condition. And the remaining 25% is the switch will be in on condition. Okay. So here we are reducing the switching stress. So from 90% to the 75%. So automatically the converter efficiency will be increases. So our main aim is to increase the voltage gain of the converter so with a lesser duty cycle.
I request any participant, you can ask your doubts orally with the directly to the resource persons. Anyone are
So if
interested
you
to
have
ask the
if you have any doubt during the modeling of the converter, you can mail to me. I will be in touch with the mail answer.
sir. I think no queries in the chat box.
Okay, okay, thank you.
Uh, thank you, sir.
Thank you.
One minute. Sir, 5 minutes, sir. HOD sir will
Okay.
come. Thank you.
Okay.
Yes. Thank you, sir. Jyotishwa, sir. I
Okay.
request HOD sir to give the vote of thanks to the resource person.
Thank you, Sunita ma'am and
Yes.
Kumar sir. Uh, yeah. Uh, Dear participants, thank you for your patience. From management of SV College of Engineering and on behalf of our Triple department, I heartfully thank to today's resource person, Mr. Dr. Jyotish Reddy. Uh, he's uh, he's one of my best friend in during the research. I know very well, sir, you about your potential. Thanks for agreeing within a short span. You agreed and you came forward and you made our session given wonderful date for us. Thank you so
Thank you,
much,
sir.
Jyotish sir. In future also, sir, we are planning a few more webinars as well as FDP, sir. We request
Okay.
you to help us, sir.
Sure, sir.
Thank you so much, sir.
Thank you, sir.
The participants, afternoon session also will be having the continuation of today's topic. So, as we said earlier also, so the afternoon session is the continuation of today morning session, and tomorrow session will be the continuation of today. So, likewise, we planned in a stream manner. So, please participate regularly. Thank you.
Thank you, sir. We request all the participants to give their valuable feedback to fill the feedback form, please.